Okay, so let's talk about a few things. I'm sure last time I had mentioned that adding a third dimension, with just a few exceptions, doesn't really change a whole lot. So, for example, if I had these two vectors, and I wanted to figure out u plus 2v, I'm going to do that the same way I did it before. So u, I got it backwards here, u plus 2v, what would 2v be? What would 2v be?
2, 4,
2, 4, 6. And then I'm going to add those together. So I'm going to add them the same way I add them in 2 dimensions. When I add vectors, what do? Just add them. So I add the x's, add the y's, add the z's. So I did a couple things there. I multiplied by a scalar. So 2v is just 2 times everything. And then I just added them together, x plus x, y plus y, z plus z. Just like we did in 2 dimensions, right? If I wanted to find a unit vector in the same direction as v, how would I do that? Well, you got to remember how you did it in 2 dimensions, because you're going to do it the same way. Who remembers how we make a unit vector? How we find a unit vector in the same direction as another vector? It's real simple. Anybody remember? We find the magnitude, and then what?
Put it on the bottom.
Divide each coordinate by the magnitude. So we're doing vector v, so we have to find the magnitude of v. Okay, now stop a minute and think about it. If you had a 2-dimensional vector, like 1, 2, what would its magnitude be? How do you find the magnitude of a vector? It's a Pythagorean theorem. So basically, you square, add them together and take the square root, right? So the magnitude of this would be root 5. Well, you do exactly the same thing in 3 dimensions, only now there's 3 numbers. So we're going to square, add them together and square root. So 1 and 4 and 9, what is that, root 14? So that's going to be the square root of 14. That's your magnitude. Same as in 2 dimensions, just a bigger Pythagorean theorem. Now we'll take each of these numbers and divide them by root 14. And there is your unit vector. I am not covering anything new here. I'm trying to show you that 3 dimensions is done just like 2 dimensions with very few exceptions. A couple of different things we'll have to look at, but most everything is the same. So if I said v dot u, how do I find the dot product? I do x times x, y times y, and now z times z, and add them up. So the dot product of these 2 vectors is 1 times negative 1, 2 times 5, and 3 times 6. And add it up, that's going to make 27. Think back, like a couple weeks ago, when you find a dot product, you multiply x times x, y times y, and add them up. Well, now it's x times x, y times y, z times z, add them up. All right, do one more, and then we'll do a couple things that are a little different. Maybe we did this yesterday, I can't remember, or whatever day I saw you, I can't remember, so we'll do this again. Find the angle between V and U? Okay, do you remember how to find the angle between V and U? There's kind of a little formula. Oh my, I did a terrible job. This is just a couple weeks ago. Find the angle between two vectors. I mean, certainly you could graph it. Now, in 3 dimensions, that's going to get a little bit more complicated. You don't need to graph it. We know that the dot product equals magnitude times cosine. Tell me that sounds familiar now that I've written it down. Yeah. We got to remember this stuff, guys, because you're going to have to do all the same problems, you know, that we did on our vector quest. Not all of them, but some of those same problems we're going to be doing again, only with 3 dimensions. So this is one of them, find the angle between the vectors. So I already did the dot product, so I already got 27. I already did the magnitude of this vector, which is root 14. Now I need the magnitude of this vector. So once again, how do we do the magnitude of a vector? Square. So 1 and 25 and 36. So what does that make? 62. Square root of 62. So the dot product, which is 27, how do we find dot product? X times x, y times y, z times z, add it up. The dot product is the magnitude of the one vector times the magnitude of the other one times the cosine of the angle between them. Now before I do the work, I like to multiply these two together so I only have one radical to deal with. It's just less parentheses. So then I'll divide. So 27 over the square root of 868 equals cosine theta. And then how do I find theta? That's my objective. I'm trying to find the angle. How do I find the angle? Yeah, second cosine. It must be radians. So I got 65.69 degrees. Is that what you got? Then you okay? Someone out there? We match?
Yeah.
Okay, good. All right, so this is just a brief, like, synopsis of things that are all the same. Now we're going to look at a few things that are a little bit different, okay? So the first thing we're going to look at that's a little bit different, did we do this yesterday? Did we graph yesterday? Okay. So the first thing we're going to look at that's a little different is we're going to sketch this. Now, wait a minute. If I had said we're going to sketch this, everybody in the room, hopefully, would know we're just going to draw a line, right? And you could draw this line lots of ways. Some of you would choose to get y by itself, y equals mx plus b, so then you'd know the y-intercept and you'd go slope up and over and whatever. Some of you might say, nah, I'm just going to plot the intercepts. So if x is 0, y would be 2. And if y were 0, x would be 3. So there's my line. That's just another way of doing it. You can do it either way, right? Now, what happens when I add a third dimension? I want you to think about this for a minute. Do you remember in the old days when we had like pull down screens in classrooms? Do you remember that? So if you want to do a video or something, you had a screen to pull down.
Yeah.
Well, if you think of that screen up here, all rolled up as the line, that's a line. If you make that three-dimensional, if you pull that screen out into the room, you don't have a line anymore. What do you have? A plane. This is the equation of a plane. I've taken a line and I've added a third dimension. So it's like taking this line right here and pulling it out. Well, when you pull it out, it makes this, which is a plane. So we've got, that's the equation of a plane now. We've added a third dimension to our line. So I'm going to graph that plane. But I'm going to graph it on the blackboard, on a plane. So it's a little bit hard to do that. So here's the axis system that we traditionally use when we graph in three dimensions. This is X, this is Y, this is Z. Now, it doesn't look like it, but all of these angles here are right angles. This is like the corner of the room. But because I couldn't draw a line out here, I had to flatten it, and so these look warped, but these are all right angles. This is the positive x-axis. The negative x-axis is back here. The negative y-axis is back here, and the negative z-axis is down here. Now, why are they drawn that way? Because you can't see them. This is a picture of this room. Think of back by the door. There are the axes. Okay, that corner is Z, here is X, here is Y. I can't see out there in the hallway, but it's out there. I can't see below me, but it's down there. All right, so I'm going to do this with intercepts. What is my x-intercept? My x-intercept is 3. So on my x-axis, I'm going to plot the point 3, 0, 0. If you let x be 3, y and z are 0. Now, I'm going to do the same thing with y. What's my y-intercept? 6. So I'll plot my y-intercept. 0, 6, 0. And my z-intercept, which is 2. Now, that's a plane, right? You learned in geometry class that it takes how many points to determine a plane? 3 non-collinear. So these 3 points are enough. So I'm going to connect them, and this is a picture of that plane. That is not hard, is it? Now, can it get harder if you're graphing things like ellipsoids? Yeah, ellipsoid would be a 3-dimensional ellipse, like an egg, an actual egg. Yes, that can get harder. I'm not expecting you to do that. Okay? There are computer things that can do that. You do have to be able to sketch a plane. Okay? It's pretty simple. All right. So then what else is different? Well, let me put 2 vectors up here, and we're going to learn a new operation that we haven't done before. So let's say vector A has coordinates 1, negative 2, 3, and B has coordinates 4, 0, 2. Now, we've already discussed A dot B. That's the dot product. Right? How do we do a dot product again? X times X, Y times Y, Z times Z, and add them up. So what is that, 10? So the dot product we've already talked about. We need the dot product if we're finding the angle between 2 lines, or 2 vectors, I mean, remember? We use dot product equals mag cosine. today we're going to look at, for the first time, the cross product. Now we haven't done a cross product, and we would say that A cross B. We haven't done a cross product because it doesn't exist in 2 dimensions. You have to have at least 3 dimensions in order to do a cross product. Okay, now when I say at least 3 dimensions, you're thinking, how many dimensions can you have? Well, in math, you can have as many dimensions as 1. In the real world, it's a little stickier, but we can have big, big vectors. We're looking at 3-dimensional vectors. So I'm going to write these vectors vertically. This is A cross B, A cross B. I'm doing the cross product, A cross B. And I'm going to write these vertically, and you will see why in a minute. You don't have to do this. Certainly other people don't do it. I think it's easier, so I'm showing you this way because I think it's easier. But here are my 2 vectors. I've just written them up and down instead of sideways. And the answer, the cross product, is going to be a new vector. Okay, now that's different because the dot product was a number. The dot product is a number. The cross product is going to be a new vector. All right, so here's what I want you to do. To find this top number right here, I want you to cover these up. Cover up the top number. I'm finding the top number. I'm going to cover up the top numbers. Now I want you to do a little cross multiply stuff. I want you to take -2 times 2, 3 times 0, and I want you to subtract them. So if you remember from last year doing determinants, that's what you're doing. You did this last year. We haven't done it yet. You may have forgotten it. It's this times this minus this times this. Okay, so that is what? -4. And that's the number that goes right there on the top. Now how do you think I'm going to find the middle number? I'm going to cover up the middle row. And I'll do 1 times 2 minus 3 times 4. So -10. And then we'll cover up the bottom. And we have 1 times 0 minus -2 times 4. 1 times 0 minus -2 times 4, so that is 8. Now, here comes the tricky part. All you have to, it's hard, you just got to remember, whatever number you got here in the middle one, you got to change its sign. So when I did the arithmetic, the middle number turned out to be 10, or -10, I need to change it to +10. Whatever is in the middle needs to be changed. If we had a bigger vector, we would change every other one. That's the rule. You change every other one. Okay? Let's try another one. Actually, let's do this.
How is 8 not negative?
Because it's 0 minus.
Let's have you see if you can do B cross A. Do B cross A, same vectors, but we're going to do it in the other direction. Tell me what happens when you cross these vectors, find their cross product. We're going to cross A and B, but do it in the other order, B and A. Okay? What happens?
The first one's positive. The other signs just changed. 4.
First one would be a 4.
The second one would be.
Middle one would be 10, but remember that's the one we changed.
Should be negative.
So it becomes -10.
And the bottom one would be -8.
Bottom one would be -8. What happened?
The signs just changed.
We got exactly the same numbers, but the signs changed. That property has a name. It's called anti-commutative. This is called the anti-commutative property. Now, everybody knows what the commutative property is, right? What do we mean when we say multiplication is commutative? What does that mean? You can do it in either order, right? So 2 times 3 is the same as 3 times 2. It doesn't matter. What do you think anti-commutative means? It's commutative, but opposite, right? So we get the same numbers, they're just opposite in sign. Okay, one more. Let me make up a couple new vectors here. Alright, so let's say vector C has coordinates 2, 3, negative 4, and D has coordinates 1, 1, negative 1. Alright, here we go. I want everybody in the room to find C cross D. Tell me what my cross product is for C cross D. Everybody's figuring it out. Compare your answer with your neighbor.
Good job.
Can you come up with an answer yet?
Yeah.
What did you get?
1, negative 2.
1?
Negative 2. Negative 1.
Alright. Do I have agreement over here on this side of the room? They seem to agree this is the right answer. Alright, so everybody's good with that.
This is the smart.
Okay. Now here's what I want you to do. I want everybody over here, on all this side over here, all you guys. I want you to take vector C and cross it with the cross product that you, not cross it, dot it. I want you to dot it, vector C, dot it with this U vector. Okay? I want you to find the dot product of this one and this one. That's what you guys do. You guys, I want you to do the same thing, but I want you to do vector D. I want you to find the dot product of this vector and your new cross product vector that you made. You're doing the dot product. So remember, how does the dot product work? X times X, Y times Y, Z times Z. Okay.
Add them all up.
Add them all up. So I want you guys doing it with vector C, and you guys doing it with vector D. So you guys are dotting this and this, just find the dot product. You guys are dotting this and this. What happened?
Got 0.
Zero. Everybody got 0. Who remembers what it means when the dot product is 0? The vectors are orthogonal, which means perpendicular. So what you just observed is that if you take 2 random vectors, I just made those up, it'll work for any random vectors, and you find their cross product, the new vector you found is perpendicular to both of the originals. So if you think about what that means, you got a vector here and you got a vector here, okay? The new vector you found is perpendicular to that one and this one. Any random vectors, the cross product will be perpendicular. Now that has implications that are pretty amazing. If you were going to write the equation of a plane, for example, containing 3 points, you would use that that concept. But for you, what do you need to know? You need to know that the cross product is perpendicular to both of the original vectors. Okay? Now, I promise you won't remember that in an hour, so if you haven't written that down, go ahead and write it down. The cross product is perpendicular, or, if you want to be real official, orthogonal to both of the originals. The cross product is orthogonal to both of the originals. All right? Now, we have one more really important thing to learn. It's new. I mean, that's a new thing. We have a couple other things to learn, but a new thing about 3 dimensions. Let's suppose we want to write the equation of the line through 1, 2, 3, and -1, 3, 7. All right? Now, I have given you 2 points. And you're going to write the equation of the line through those 2 points. Okay? Now, you've been writing equations of lines for a long, long time. What does it take to write the equation of a line? Well, it takes a point, any point, and the slope. Now, points are not an issue. I've got my points. The slope is going to be an issue. Because why? What's slope? Definition. Y over x. Change in y over change in x. We have a problem here because we have z's that have to be dealt with. When we write the equation of a line in 3 dimensions, then we have to do it a little differently. There are 2 formats that we're going to use. One is called the vector form of the line. And it looks like this. This is called the vector form or the vector representation of the line. Representation. Okay, the vector form or the vector representation of the line. In this first blank right here is your starting point. You're writing the equation of a line, so you have to have a point. In 2 dimensions or 3 dimensions, you have to have some place to start, and then you can move from that point. So I'm just going to pick 1, 2, 3. I could have picked -1, 3, 7. It doesn't matter. I have to pick one of my points. Just like in 2 dimensions, you have to have a point to start with, and then you move from there, right? Now, this is going to tell me how to move. How does this line move? Well, it goes from 1 to -1, which is back 2. It goes from 2 to 3, which is up 1. And it goes from 3 to 7, which is 4. So, is this thing kind of like slope? It's describing up and over and all around, but it's got 3 dimensions, so I can't make it a fraction, but it's like slope. It's actually called the direction vector of the line. It tells me how the line moves. So, these are the increments, and getting from this point to this point, these are the size of the steps that I would take. If I put a multiplier in front of that, I could double that, or half it, or -2 it. So if I put all these different multipliers, I would generate all different points on this line. Does that make sense to you? If I let TB1, I'm going to end up at exactly this point. If I let TB2, I'm going twice as far. Okay. So that's the vector representation of the line. When you write the equation of a line in 3 space, one way to do it is with the vector representation. The other way to do it is parametrically. The parametric equations. Now you've seen those before. X equals, Y equals, and now Z equals. So look at your vector form right here. Look at the beginning of everything. So X equals 1 minus 2t. X equals 1 minus 2t. That's your first parametric equation. See how I built that? So what's Y gonna equal?
2 plus 1.
2 plus 1t. And Z will be
3 plus
4t. So there are your parametric equations. So you know how in 2 dimensions you can write a line in slope-intercept form,
Yeah.
you can write a line in point-slope form, you can write a line in standard form. Well, in 3 space we use either the vector form, which is this, or we use the parametric form. They're the same, they're just split up differently.
And then will we have to get out of
Can we only find the parametric forms if we have the direction?
Yep. Yep.
I mean, the
Yep.
vector.
Because the coefficient, well, you wouldn't necessarily have to write this down, although I always do. But you definitely need to have your direction vector because those are the coefficients on the T. So you have to do this work whether you actually physically write it down or not. That's up to you. Okay? All right. I think I have talked about absolutely everything I need to talk about with you guys. Your homework, by the way, is due Monday.
That is huge.
Monday. Except one, what?
That's huge.
What?
So the bonus is.
It's due Monday?
Yeah.
Yeah.
Bonus would be
Yeah, I thought it was gonna be due tomorrow, but I can't.
Yeah, that's pretty good. Bonus, you mean
So, here we go. The last thing we have to talk about. Let's look at, there's one more piece of the conic sections puzzle that I have not included yet, and I need to. So let's do a review problem. It won't hurt us certainly to do a review problem. And I apologize if this is one we've already done, because I haven't kept track of which ones I've done or not. So let's do this one. All right, it won't hurt us to do it again if we've already done this one. What is this?
that's a hyperbola.
This is
Hyperbola. Hyperbola. It's a hyperbola. It's a hyperbola.
Oh yeah, hyperbola.
It's a hyperbola.
Hyperbola.
Now, if you get confused, did we talk about the rotations the other day?
Yeah.
So, if you get confused, could you do your discriminant on this? Absolutely. B squared, now there's no xy in here, so I know this is a hyperbola. I can tell. But if you forget that, you can do this. Remember, B is the coefficient on xy. You don't have one. A is -9. And C is 4. Is that answer, you don't have to figure it out, is it positive or negative? That's going to be a positive answer. And when the discriminant is positive, you have a hyperbola. So, this one, I can look at it and tell you it's a hyperbola. But if you can't, you forget, don't trust yourself, whatever, do the discriminant, it will never be wrong. I mean, the discriminant will work in every equation. Okay? All right. So, we know it's a hyperbola. So now we're going to put it into standard form. So remember how we do that. Group our y's and pull out a 4. We group our x's and pull out a -9, and this is where things get hairy. That would be x squared minus 2x.
Ooh, it's getting hairy,
Right? So now we put a 9 here, but that 9 is really a 36. We put a 1 here, but that's
Minus
really
one.
a minus 9.
Divide by 36.
Divide everything by 36. And there we have our hyperbola. Alright, so now let's do what we do. Because I'm going to have to erase part of this. So everybody's good on this?
Yeah.
Alright, so I'm going to erase this stuff right here. And we're going to find our stuff. And we're going to find something new. We're going to find something new. But we're going to start with the center like we always do. Be very careful. What's your center?
1 negative 3.
1 negative 3. Several quizzes, we got things backwards, and that of course throws everything off. Be careful. 1 negative 3. What's that 9 right there? Tell me.
Tell us to go up and down.
Up
3.
and down. It's under Y, so it's up and down 3s. So 1 0. 1 negative 6. And the 4 tells me
Side to side 2.
side to side 2. Now this is a hyperbola, so don't get wild and crazy. Don't connect all those dots with an oval.
Box.
You want to connect all those dots with a box. Yeah, it's going to be a rectangle. If the box happens to be a square, Griffin, your hyperbola is called equilateral. It's called an equilateral because that would mean these two numbers were the same. Alright, now we got to open our hyperbola one way or the other. Pay attention now. Which way is this one going to open?
Up and down.
Up and down. So up it goes. Down it goes. Here we are. Now, I'm going to put my foci on there. Well, first of all, let's get major or transverse axis and conjugate axis. The transverse axis is the one that joins the vertices, so it is 6. The conjugate axis is 4. These should be easy points, that's why I put them on there. Alright? Now, your foci, here they are, inside the curve, behind the vertices. The vertices, by the way, are the points 1, 0, and 1, negative 6. Those 2 points are your vertices. Now I'm finding my foci. And in order to find the foci, I need to know how far it is from the center to the focus. The distance from the center to the focus is root 13. So I'm going to start right here at the center. And I'm going to go up root 13. So this is going to be 1 comma negative 3 plus root 13. And 1 comma negative 3 minus root 13. Now it's at this point I want to introduce this new concept, which if you've been doing your homework, you've run into the word. Anybody know where I'm going? Eccentricity. Eccentricity.
Isn't it like C over 100 or something?
Okay, there is a, yes, Griffin, you're very close there. There is a, or you're on the right track, absolutely. There is a constant associated with every conic section called its eccentricity. Now I'm going to do 2 things here. I'm going to give you the formal definition of the eccentricity, and then I'm going to show you how we find it, because we don't find it using the definition, but I want you to have the definition. Eccentricity is a fraction. Okay. And it is the distance, the numerator is a fraction. So the top is the distance from a point on the curve to the focus divided by the distance from a point on the curve to the directrix. That's the formal definition. Now, we can't use the formal definition because while everybody in here could find the distance from point on the curve to the focus, we haven't talked about the directrices of the ellipse and the hyperbola, and we're not going to. They have directrices. For a hyperbola, they would look like that. They're between the two curves. We're not going to do those. So this is the formal definition. So on the test, if it says define eccentricity, there it is. Now, how are we going to find it? We're going to find it by taking the distance from the center to the focus and dividing it by the distance from the center to the vertex.
Which one do we know? Both or what?
You know both. This is the actual definition. This is how we are going to calculate it. Okay? Now, do I know for this hyperbola, do I know the distance from the center to a focus?
Yes.
Yes, that's root 13. What about center to vertex? Do I know the distance from the center to the vertex?
Yes.
Yes. What is it?
3.
3. There is your eccentricity. Now, what can you tell me about the size of that fraction? Is that fraction bigger than 1 or less than 1? Now, think about it. In a hyperbola, does it make sense to you that center to focus over center to vertex will be a number bigger than 1?
Yes.
Now, let's think about our friend the ellipse.
That seems less than
Center to focus over center to vertex. Tell me about that fraction. That's going to be less than 1.
Yeah.
Let's think about our hyperbola, or our parabola. We have a parabola. We know here's the focus, and we know here's the directrix, right? All right. Now go back to the original definition. Distance from point on curve to focus, distance from point on curve to directrix. What do we know about these two distances?
They're going to be equal.
They're going to be equal. So the eccentricity of a parabola is always going to be 1. Every parabola has an eccentricity of 1 because that's its definition. Equidistant from focus and directrix. Equidistant. So the ratio is going to be 1. Every parabola has an eccentricity of 1. Every hyperbola has an eccentricity bigger than 1. Every ellipse has one less than 1. You have to calculate them. What about a circle?
Yeah, which one do you have? Half?
Which one's greater than
0.
The foci of a circle have converged at the center, so the distance from the center to a focus is 0. 0. So a circle, taking our test, we've done an eccentricity blank for every one of them.
Alright.
If it's a circle, you put a 0. If it's a parabola, you put a 1. If it's an ellipse or a hyperbola, you have to build your fraction. But if you've already done that work, you have these two numbers already. You've already figured those two numbers out. Okay? Oh, Lordy, I think I covered everything. You start working on your homework and let me know. I did your quizzes and put them in. We'll get them back when we have more people here.